move on to our next topic. So, our next topic has come up right after ARP because while studying about ARP, you must have realized that I told you that ARP has no sort of validation. So, how could that exactly be fixed? So, if the data that actually is being transferred over LAN is encrypted using cryptography, ARP can actually be used very validly. I mean, what you want to do is you want to hide what you're actually sending before sending it out on a local network so that people who are not supposed to get it can't actually see it. Now, let's first tackle the question, what exactly is cryptography? So, cryptography is basically the art of hiding anything. Now, when talking about computers and computer science in general, it includes hiding data. So, now cryptography doesn't really actually start with the new age. It's been there for a long, long time, since the time of Julius Caesar and all. We'll be talking about the history of cryptography right now. But what I want you to understand is that when a message is sent, a key is actually used along with an encryption algorithm. Now, this key is also sent to the other person, and how this key is sent, we'll get into that later. So, what you want to basically understand for now is a message is encrypted using an encryption algorithm, which takes the key and the message as parameters. Then, on the other side of the message, with the ciphertext, that is, after encryption, you get something called ciphertext because it has to be deciphered now. So, cipher is just a word, a Latin word, I guess, or a Greek word. I'm not really sure. That means to hide. So, first you encrypt your message, then you decrypt your message with the ciphertext and the decryption key, which is most of the time the same as the encryption key when we're talking about symmetric key cryptography. So, use the decryption key and the message along with the decryption algorithm, and you get the same message on the other side. So basically, it's like a password. It's a password protect for messages, and it's a fancy way to say that, and that is cryptography. So let us go into the history of cryptography now. So let me give you a brief history of cryptography. Now, cryptography actually goes back several thousand years before, shortly after people began to find ways to communicate. There were some of us who were finding ways to make the understanding of that communication difficult so that other people couldn't understand what was going on. And this led to the development of Caesar cipher that was developed by Julius Caesar. And it's a simple rotation cipher. And by that, I mean that you rotate a portion of the key in order to generate the algorithm. So here's an example. We've got two rows of letters and that are alphabetical in order, and means we basically written the alphabets down and the second row is shifted by three letters. So a B is a Z actually, because if you move that way, a B is a Z from the first row gets shifted back to the second row, and then the letter D becomes the letter C. That's an example of how encryption works. So if you try to encrypt a word like hello, it would look completely gibberish after it came out of that algorithm. So if you count the letters out, you can see that the letter H can be translated to letter L. So that's a Caesar cipher. Now you must have heard of things like ROT13, which means that you rotate the 13 letters instead of 3 letters. That's what we can do here again. And this is just a simple rotation cipher or Caesar cipher. That's what, of course, the ROT stands for. It's rotate or rotation. Now, coming forward a couple thousand years, we have the Enigma cipher. Now, it's important to note that the Enigma is not the word given to this particular cipher by the people who developed it. It's actually the word given to it by the people who were trying to crack it. The Enigma cipher is a German cipher. They developed this cipher and a machine that was capable of encrypting and decrypting messages so that they could messages to and from different battlefields and war fronts, which is similar to the Caesar cipher. Caesar used it to communicate with his battlefield generals, and the same thing with the Germans. You've got to get messages from headquarters down to where the people are actually fighting, and you don't want it to get intercepted in between by the enemy. So therefore, you use encryption. And lots of energy was spent by the Allies, in particular the British, trying to decrypt the messages. One of the first instances that we are aware of where a machine was used to do the actual encryption, and we're going to come ahead a few decades now into the 1970s, where it was felt that there was a need for a digital encryption standard. Now, the National Institute of Standards and Technology is responsible for that sort of thing, so they put out a proposal for this digital encryption standard. And an encryption algorithm, what ended up happening was IBM came up with this encryption algorithm that was based on the Lucifer cipher. That was one their people had been working on a couple of years previously in 1974. And they put this proposal together based on the Lucifer cipher, and in 1977, that proposal for an encryption algorithm was the one that was chosen to be the digital encryption standard, and so that came to be known as DES over time. And it became apparent that there was a problem with DES, and that was it only had a 56-bit key size. And while in the 1970s that was considered adequate to defend against brute forcing and breaking of code, by 1990s it was no longer considered adequate, and there was a need for something more, and it took time to develop something that would last long for some long period of time. And so, in the meantime, a stopgap was developed, and this stopgap is what we call the triple DES. The reason it's called triple DES is you apply the DES algorithm three times in different ways, and you use three different keys in order to do that. So, here's how triple DES works. Your first 56-bit key is used to encrypt the plain text, just like you would do with the standard digital encryption standard algorithm, where it changes, and you take that ciphertext that's returned from the first round of encryption, and you apply the decryption algorithm to the ciphertext. However, the key thing to note is that you don't use the key that you use to encrypt. You don't use the first key to decrypt it because otherwise you'll get the plain text back. So what you do is you use a second key with the decryption algorithm against the ciphertext from the first round. So now you've got some ciphertext that has been encrypted with one key and decrypted with the second key, and we take the ciphertext from that and we apply a third key using the encryption portion of the algorithm to that cipher. Encryption portion of the algorithm to that ciphertext to receive a whole new set of ciphertext, obviously. To do the decryption, you do the third key and decrypt it. With the second key, you encrypt it. And then with the first key, you decrypt it. And so you do reverse order and the reverse algorithm at each step to apply triple DES. So we get an effective key size of about 168 bits, but it's still only 56 bits at a time. Now, I said triple DES was only a stopgap. What we were really looking for was the advanced encryption standard once again. And NIST requested proposals so that they could replace the digital encryption standard in 2001. After several thousands of looking for algorithms and looking them over, getting them evaluated and getting them looked into, NIST selected an algorithm and it was put together by a couple of mathematicians. The algorithm was called Reindoll, and that became the Advanced Encryption Standard, or AES. It's one of the most advantages of AES is it supports multiple key lengths. Currently, what you'll typically see is as we are using 128-bit keys. However, AES supports up to 256-bit keys. So if we get to the point where 128-bit isn't enough, we can move all the way up to 256 bits of keying material. So cryptography has a really long history. Currently, we are in a state where we have a reasonably stable encryption standard in AES. But the history of cryptography shows that with every set of encryption, eventually people find a way to crack it. Okay, so that was a brief history of cryptography. Now, what I want to do is let's go over and talk about AES, triple DES, and DES in themselves because they are some really key cryptographic moments in history. Because there's some really key historic moments in the history of cryptography. Now, we're going to talk about the different types of cryptographic ciphers, and primarily we're going to be talking about DES, triple DES, and AES. Now, DES is the digital encryption standard. It was developed by IBM in the 1970s, and originally it was cryptographic cipher named Lucifer. And after some modifications, IBM proposed it as the digital encryption standard, and it was selected by the digital encryption standard. Ever since then, it's been known as DES. Now, one thing that caused a little bit of controversy was during the process of selection, NSA requested some changes, and it hasn't been particularly clear what changes were requested by the NSA. There has been some speculation that wondered if the NSA was requesting a backdoor into this digital encryption standard, which would allow them to look at encrypted messages in the clear. So basically, it would always give the NSA the ability to decrypt DES encrypted messages. It remained the encryption standard for the next couple of decades or so. So, what is DES and how does it work? Basically, it uses 56-bit keys rather than a stream cipher. It's a block cipher and it uses 64-bit blocks. And in 1998, DES was effectively broken. When a DES encrypted message was cracked in 3 days, a year later, a network of 10,000 systems around the world cracked the DES encrypted message in less than a day. And it's just gotten worse since then with modern computing power being what it is. Since DES was actually created, we already had come to the realization that we needed something else. So along came triple DES. Now, triple DES isn't three times the strength of DES necessarily. It applies DES just three times. And what I mean by that is what we do is we take a plain text message Then let's call that P, and we're going to use a key called K1, and we're going to use that key to encrypt the message. And use a key that we will call K1, and we're going to use that to encrypt the message. And that's going to result in the ciphertext, and we'll call this C1. So C1, the output of the first round of encryption, we're going to apply a second key, and we'll call that K2 with that second key. And we're going to go through a decryption process on C1. Since it's the wrong key, we're not going to get plain text out on the other end. What we're going to get is another round of ciphertext, and we will call this C2. What we do with C2, we are going to apply a third key, and we will call this K3, and we're going to encrypt ciphertext C2, and that's going to result in another round of ciphertext, and we will call that C3. So we have three different keys applied in two different ways. So with key 1 and key 3, we do a round of encryption, and with key 2, we do a round of decryption. So it's an encrypt, decrypt, encrypt process with separate keys. While that doesn't really yield a full 168-bit key size, the three rounds of encryption yields an effective key size of 168 bits because you have to find 356-bit keys. So speaking of that, technical detail for triple DES, we're still using the DES block cipher with 56-bit keys, but since we've got three different keys, we get an effective length of around 168 bits. Triple DES was really just a stopgap measure. We knew that if DES could be broken, triple DES could surely be broken with just some more time, I guess. And so the NIST was trying to request a standard that was in 1999, and in 2001, NIST published an algorithm that was called AES. So this algorithm that was originally called Raindoll was published by NIST as the Advanced Encryption Standard. Some technical specifications about AES is that the original Raindoll algorithm specified variable block sizes and key lengths. And as long as those block sizes and key lengths were multiples of 32 bits, so 32, 64, 96, and so on, you could use those block sizes and key lengths. When AES was published, AES specified a fixed 128-bit block size and key length of 128, 192, and 256. AES with three different key lengths, but one block size. And that's a little bit of detail about DES, triple DES, and AES. So when AES was published, AES specified a fixed 128-bit block size and a key length of 128, 192, and 256 bits. So we've got with AES three different key lengths, but one block size. And that was a little bit of detail about DES, triple DES, and AES. We'll use some of these in doing some hands-on work in the subsequent part of this video. Okay, so now that I've given you a brief history of how we have reached the encryption standards that we are following today, that is the Advanced Encryption Standard, let's go ahead and talk a little bit more about DES, triple DES, and AES. So DES is a digital encryption standard. It was developed by IBM in the 1970s, and originally it was a cryptographic cipher named Lucifer. And after some modifications, IBM proposed it as the digital encryption standard. It was selected to be the digital encryption standard, and ever since then, it's been known as DES or DES. One thing that caused a little bit of controversy was during the process of selection, the NSA requested some changes, and it hasn't been particularly clear what changes were requested by the NSA. There has been some sort of speculation that wondered if the NSA was requesting a backdoor into this digital encryption standard, which would allow them to look at encrypted messages in the clear. So basically, it would always give the NSA the ability to decrypt DES encrypted messages. It remained the encryption standard for the next couple of decades or so. And what is DES and how does it work? Now, DES remained the digital standard for encryption for the next couple of decades. So what does it do and how does it work? So basically, it uses a 56-bit key rather than a stream cipher. It's a block cipher and it uses 64-bit blocks. And in 1998, if you know, DES was effectively broken when a DES encrypted message was cracked in 3 days. And then a year later, a network of 10,000 systems around the world cracked a DES encrypted message in less than a day. And it's just gotten worse since then with modern computing being what it is today. Now, since DES was created and broken, we knew we needed something. And what came in between advanced encryption standards and DES is triple DES. Now, triple DES isn't 3 times the strength of DES necessarily. It's really DES applied 3 times. And what I mean by that is we take a plain text message, then let's call that P, and we're going to use a key called K1. And we're going to use that key to encrypt the message, and that's going to result in the ciphertext 1. So we'll call that C1. Now, C1 is the output of the first round of encryption, and we're going to apply a second key called K2. And with that second key, we are going to go through a decryption process on C1. Now, since it's the wrong key, we are not going to get the plain text out of the decryption process on the other end. We are going to get another round of ciphertext. And we're going to call that C2. Now with C2, we are going to apply a third key and we are going to call that K3. And we're going to encrypt ciphertext C2 and that's going to result in ciphertext C3. So we have three different keys applied in two different ways. So with key 1, key 3, we do a round of encryption. With key 2, we do a round of decryption. So it's basically an encrypt, decrypt, encrypt process with three separate keys. But what it does really is it doesn't really yield a 168-bit key size because in effectiveness, it's basically 56-bit keys that are being used thrice, whether it be three different keys. So in effectiveness, you could say that it's a 168-bit key, but it is not the same strength because people realize that triple DES can be easily broken because if DES is broken, you can do the same thing with three different ways with whatever key that you use. So it just takes longer time to decrypt if you don't know the key and if you are just using a brute force attack. You know that triple DES can be broken if DES can be broken. So triple DES was literally a stopgap between DES and AES because people knew that we needed something more than triple DES. And for this, the NIST or the National Institute of Standards and Technology in 2001, they chose AES as the algorithm that is now called the Advanced Encryption Algorithm. So it was originally called the Raindoll algorithm. And the main thing about the Raindoll algorithm and the Advanced Encryption Standard algorithm is that the Raindoll algorithm specifically states in its papers that it has a variable block size and a variable key size as long as they are in multiples of 32. So 32, 64, 96, like that. But what AES does differently is that it gives you one block size that is 128 bits and gives you three different key sizes that is 128, 192, and 256. So with AES, three different key lengths, but one block size. Okay, so that was a little bit more information on AES, DES, and triple DES. And we are going to be using this information in some subsequent lessons. Okay, now moving on. Okay, so now that we've discussed the different history of cryptography and the more important cryptographic algorithms, let's discuss the different types of cryptography. Now, the first type of cryptography I'm going to talk about is symmetric cryptography. And by symmetric cryptography, I mean that the key is the same for encrypting or decrypting. So I use the same key whether I am encrypting the data or decrypting the data. One of the things about symmetric key cryptography is that they use a shorter key length than for asymmetric cryptography, which I'll get into a couple of minutes. It's also faster than asymmetric, and you can use algorithms like DES or AES, as those are both symmetric key cryptography algorithms, and you can use a utility like AES script. Let me just demonstrate how symmetric key cryptography works. So for this, we can use a tool called AES script. So in AES script is actually available for Linux and Windows and Mac, all the systems. So I'm using it on the Windows one and I'm using the console version. So first of all, I have a text file called text.txt. So let me just show that to you. So as you guys can see, I have this thing called text.txt. Now to do text.txt, let me just show what text.txt contains. So as you guys can see, it has a sentence called "The quick brown fox jumped over the lazy dog." So that's the sentence that has all the alphabets in the English language, rather. So now we are going to try and encrypt it. So we can use something like AES or DES because both of them are symmetric key ciphers, symmetric key algorithms, rather. So we are using AES in this case. So what we're going to do is say AES script. We're going to encrypt it and we're going to use a password of, let's say, Pokemon. So we're going to call it Pokemon and we're going to do text.txt. We're going to encrypt that file. So now we have encrypted that file. Now let's go see. We must be having a new file. So this is called text.txt.aes. So that is our encrypted file. And this is what we would generally send over the network if we are sending it to anybody. So let's assume the person who's received it also knows our encryption algorithm. I mean, encryption algorithm and the key that goes along with it. So let's try to decrypt it now. Now, before I decrypt it, let me just show you what an encrypted message looks like. So this is what the ciphertext looks like. Type text.txt.aes. So yeah, as you guys can see, the Windows console can't really read everything, but if I were to go here, if I were to just go into the file and just edit with Notepad++, you'll see that it's a bunch of crap. you really can't make out anything. What is being made here, we can't really decipher much. So that's the point of using encryption. Now, if you were to decrypt it, all we have to do is AES crypt. We're trying to decrypt. We're trying to give the password is going to be, what was the password? Pokemon. Okay, so, and we're going to try and decrypt text.txt.aes. Let's dir that again. Okay, so that just decrypts our message for us. So this is how you would use AES script for encryption and decryption. So that just decrypts it, and that's how you would use symmetric key encryption to encrypt a file for this example. Symmetric key uses either a stream cipher or a block cipher, and the differences between stream or block ciphers is that block takes a block of bits at a time, and it's a fixed length. So for example, 64 bits, if I were to use a block cipher with 64 bits, I would need to take in 64 bits before I could start encrypting. Now, if I didn't have 64 bits to encrypt, I would have to fill it with padding in order to get up to 64 bits a stream cipher. On the other hand, it will encrypt a bit at a time, so it doesn't matter how many bits you've got. You don't need to have some multiple of the block length in order to encrypt without padding. And another type of cryptography is asymmetric. Now, asymmetric, as you would expect, uses two different keys, and that's where we have public key and private key. Asymmetric key cryptography uses a longer key length, and it also has more computation, and the encryption process is slower with a symmetric key encryption. And the encryption process is slower than with the symmetric key encryption. One of the uses for symmetric key is for signing documents or emails, for example, where I would have the private key sign something and the public key would be used to verify a signature. And another reason for using asymmetric key encryption is to ensure that you got it from who actually sent it. Since you've got two keys, you always know who the other end of the equation is. Where with symmetric key, since it's just one key, if you can intercept the key, you can decrypt and also encrypt messages. And so if somebody can figure out the key, you can break into a communication stream using symmetric key encryption. So asymmetric gives you the advantage of ensuring that the other end is who the other end says. And they are, since they're the only ones who should have the private key. And in this particular instance, in practice, however, hybrid encryption models tend to be used, and that's where you would use asymmetric encryption to encrypt asymmetric session keys. So basically, you encrypt the message that you are sending using symmetric key encryption. And then when you're exchanging the key with somebody else, you use asymmetric key encryption. So this is going to be a slower process. You probably won't want to use it for smaller files. In order to do that, fortunately, the file example that I have is a smaller one. So I'm going to try and generate a key right now. So for this, we have to head over to our Ubuntu system. So let's see. Let me show you how public key encryption actually works. And we are going to first create a key. So let me just clear this out for you. So first of all, let's create a file and let's call that text.txt. Now, if you see, we are going to edit text.txt to have some file. So have some text in it. So there seems to be a warning with the GTK. I'll just use echo instead. So now let's see if that is in our file. Okay, so let me just show you how asymmetric key encryption or public key cryptography works. So first of all, we need a text file. So let me see. Do we have a text file? So there seems to be a text.txt. So let's see what this text.txt says. So it says that this is a random text file. Now what we want to do is we want to create a public key first. So I'm going to use OpenSSL for doing this. So we go OpenSSL and we are going to use it with RSA. So we're trying to generate a key, so gen RSA, and we're going to use des3 to use this, and we're going to output it into a file called private.key. So we are also going to be using a 4096 bit. So this is going to be our private key. So this will create a private key using RSA algorithm. So let it work its way out. So first of all, it's asking me for a passphrase now. So since you can protect your keys with a passphrase, so I'm just going to use my name. Okay, so now we see if we ls and we have a private dot key, I guess. Yep. So we have this private dot key. Now we're using this private key, we are going to generate a public key. So for this, I'm again going to be using OpenSSL. And OpenSSL is a Unix based, so you will need a Unix system. So you go RSAUTL, that's RSA utility, and what we want to do is encrypt, and we want the public key in key, and we want to use the public key that we just generated. I'm sorry, guys. So we are going to be using RSA. So first of all, we need to generate a public key. So for that, we use the private key. So we will give the private key as an argument after the in flag. So private dot key, and we are trying to get out a public key. So pub out, and we're going to call it public dot key. Okay, so there seems to be. Okay, I messed it up a little. I forgot to give the output. So you go out, and then you use public dot key. So it's asking me for my passphrase, and now it's writing the RSA key. And since the password was correct, we have a public key too. So if you see, now we have a public key and a private key. So we are going to encrypt our file using the public key. So we go OpenSSL, and we go RSAUTL, and we go encrypt, and we can do pub in. So we are going to use the public key, and we want to put the text.txt as the file to be encrypted. So text.txt. And what we want to output is an encrypted file. So encrypted.txt. Okay, I call it OpenSLL. I need to go and edit that out now. Yeah, so that makes it a correct command. And now we have an encrypted file. So let's see. Alice and yep, encrypted.txt. So if we just cut that out, so we see it's a bunch of garbage and we really can't read it unless we decrypt it. So for decrypting the key, all we have to do is again use OpenSSL. Let's clear this out first. So OpenSSL, and we are going to be using the RSA utility again. So RSA UTL, we're going to decrypt this time. So we go with the decrypt flag, and then we are going to be giving the in key, and that is going to be the private key. And what we want to decrypt is encrypted.txt. And what we want to output it is as, let's say, plaintext.txt. So it's going to ask me for my passphrase, which is my name, and I've entered the passphrase, and now we have a plaintext.txt. Now, if we are to go in ls, we see that we have a plaintext.txt out here, just beside info.txt. Now let me just cat that out. So plaintext.txt. So this is a random text file. And if we go up, we see that it was a bunch of garbage, and before that, it was a random text file. Now, you can also run this command called diff plaintext.txt text.txt. So this will give you a difference in the text strings. So it's 0, so it gives you that's the difference. So both the files are the same, and that's how public key cryptography works and how symmetric key cryptography works. Okay, now moving ahead of cryptography, let's talk about certificates. Okay, so now that we're done with cryptography, let's talk about digital certificates. So what is a digital certificate? Well, a digital certificate is an electronic password that allows a person, organization to exchange data securely over the internet using public key infrastructure. So digital certificate is also known as a public key certificate or an identity certificate. Now, digital certificates are a means by which consumers and businesses can utilize the security application of public key infrastructure. Public key infrastructure comprises of the technology to enable and secure e-commerce and internet-based communication. So, what kind of security does a certificate provide? So, firstly, it provides identification and authentication. The person or entities with whom we are communicating are really who they say they are. So that is proved by certificates. So then we have confidentiality. The information within the message or transaction is kept confidential. It may only be read and understood by the intended sender. Then there's integrity, there's non-repudiation. The sender cannot deny sending the message or transaction. The receiver, we'll get to non-repudiation, and I'll explain how non-repudiation comes into digital certificates. So digital certificates are actually issued by authorities who are business, who make it their business to actually certify people and their organization with digital certificates. Now you can see these on Google Chrome. Now let me just open Chrome for you guys, and you can see it out here. You can see certificates, and you can go into the issuer statements, and you can go into all sorts of stuff. So you can see it's issued by Encrypt Authority X3. So that's an issuing authority for digital certificates. Now, that was all about the theory of certificates. Let's go and see how you can create one. So to create a digital certificate, we are going to be using the OpenSSL tool again. So first of all, let me show you how to create a certificate. So we are going to be using the OpenSSL tool for that. So first of all, let me clear the screen out. So in this case, I'm going to generate a certificate authority certificate. So I'm doing an RSA key here to use inside the certificate. So first of all, I need to generate a private key. So to do that, as I had just showed you guys, we can use the OpenSSL tool. You go OpenSSL and gen RSA, and we're going to use dest3. Then we're going to out it, and let's call it ca.key. And we're going to use 4096 bits. So I'm doing an RSA key here to use inside the certificate. So I'm generating a private key, and the private key is used as a part of the certificate. And there's a public key associated with the certificate. So you've got public and private key, and data gets encrypted with the public key and then gets decrypted with the private key. So they are mathematically linked, that the public and private key, because you need one for the end of the communication, and the other for the other end of the communication. And they have to be linked so that the data that gets encrypted with one key gets to be decrypted with other key. So this is asking for a passphrase, and so I'm going to be giving my name as a passphrase. So that has generated the key for us. So now I'm going to generate the certificate itself. So I'm going to be using the OpenSSL utility. So first of all, you say OpenSSL, and you say request. So it'll be a new request, and it's going to be an X509 request. It's going to be valid for 365 days. And let's see, the key is going to be ca.key. And we're going to output it into CA, or let's call it edureka.crt. So this is a certificate that I'm producing in the name of the company that I'm working for. So that is edureka. So it says it's unable to load the private key. Let me just see, is the private key existing? I had a previous private key, so let me just remove that. Does it have a ca.key? Seems like I put the name differently. So let me just try that again. Open SSL. Then we do request. So we're requesting a new certificate, and it's going to be X509, and it's going to be there for 365 days. And key is ca.key. Apparently that's what it's called out here. So, and it's going to be out into edureka.crt. Let's see if that works. So let's enter the passphrase. So it's my name. So now it's going to ask me a bunch of information that's going to be inside the certificate. So let's say it's asking the country name. Again, so let's put in the state. Okay, so IN, state, province name, some state. So Bangalore. Locality, let's say Whitefield. Organization name is Edureka. Unit name, Brain Force. Common name, let's leave that out. Email address, let's leave that out too. And we have our certificate. So if you go and list out your files, you'll see that there is a certificate called edureka.crt out here, which is highlighted. Okay, so now if you want to view this file, you could always use the OpenSSL. You could always use the OpenSSL utility. So you say you want to read an X059 request and you want it in text, and what you want to see is edureka.crt. Okay, so that is the certificate. So you see that it has all the signature, it has signature algorithm, it has all the information about the certificate, and it says signature issuer is CIN in state Bangalore, in location Whitefield, Edureka Brainforce, validity. It has all sorts of information. So that was all about digital certificates, who issues digital certificates, where are they useful. So this is basically non-repudiation. So nobody can say with this certificate that if this certificate is included in some sort of a website, and that website tends to be suppose malicious, and there's a complaint. Now the website can't go to a court of law and say they didn't know about this, because the certificate that was included had their private key, and the private key was only supposed to be known to the company. So that is non-repudiation. You just can't deny that you didn't do it. Okay, so that was all about certificates. Now moving on. Okay, so moving on, we are going to be talking about cryptographic hashing. Now, while the word cryptographic is in the term cryptographic hashing, and it does lead you to believe that there is encryption involved, there is no encryption involved in a cryptographic hash. There is a significant difference between hashing and any sort of encryption, and that is primarily that encryption is a two-way process. When I encrypt a piece of data or a file or anything else, What I'm doing is putting it into a state where I expect it to be able to get it back out again. In other words, when I encrypt a file, I expect it to be able to decrypt the file and get the original contents. Hashing is a one-way function on the other hand. Once I've hashed a piece of data or a file, there is no expectation and ability to get the original piece of data back. Hashing generates a fixed length value, and different types of hashing will generate different length values. For example, MD5 will generate a different length value than SHA-1, and they're both hashing algorithms, but they generate different length values. And the resulting value from a hash function should be in no relation at all to the original piece of data. As a matter of fact, if two inputs generate the same hash value, it's called a collision. And if you can generate collisions, you may be able to get a point where you can generate a piece of data that are going to generate the same hash values, and that leads you to the potential ability to break the particular hashing algorithm that you're using. So what we can use hash is for, well, one thing we can use hash is for file integrity. We can run a hash on a file and get a value back, and later we can check that the value to make sure if it's the same. If it's the same, I can be sure that the same file was hashed in both instances. So let me just show you an example of what I just said, that if we hash a file, we'll get the same hash every time. So remember the certificate that we just created? Let me just log in again. So we are going to hash this certificate, and it will create a certain hash. And we are going to see that every time we hash it, we are getting the same hash. So we can use this command called md5 sum, and we can do edureka.crt. So this is the hash produced after you've hashed edureka.crt. So if I do an MD5 again, so MD5 is a hashing algorithm that you should know of. So edureka.crt, and it will produce very similar hash. Let's see if SHA-1 works like this. So SHA-1 edureka.crt. Okay, SHA-1 is the SHA from the SHA utils package. Okay, so I've proved my point that with MD5, which is a cryptographic hashing algorithm, we are getting the same hash back. So if you are able to produce the same hash, that means you have broken the algorithm in itself. So if you run MD5 on Linux, you can get a version of MD5 and MD5 summation program on Windows and Mac OS, where with the utility MD5, which does the same thing. So I just showed you the file and I hashed it. And another reason we use hashing is we are storing passwords. So passwords are stored after hashing. We hash the passwords, and the reason for hashing passwords is so you're not storing the password in clear text, which would be easily seen even if you got it protected with permissions. If I hash the password every time I hash that password, I'm going to get the same value back from the same algorithm. So what I do is store the hash in some sort of password database. Since it's a one-way function, you can't get the password back directly from the hash. Now, what you can do with most password cracking programs, do some variation of this, and you just generate hashes against a list of words until you get a hash value that matches the one in the password. Once you get the hash that matches the one in the password, you know what password is there and here. And we come back to the idea of collisions. If I can take two different strings of characters and get the same values back, then it's easier to crack the password, because I may not necessarily get the password, but if the hash that I get back from a particular string of data is the same as that I get from the original password, then it doesn't matter whether I know the password, because the string of data that I put in is going to generate the same hash value that you're going to compare when you log in. And this hash value will just give you that it's valid, and you'll be able to log in. So suppose the password that you chose while making your account is dog, and the dog word produces this hash value. And if I were to like hash cat with the same algorithm, and if the algorithm was prone to collisions, it might produce the same hash value as dog. So with the password cat, I could open up your password. I could open up your account. So that was all about hashing and hashing algorithms. Let's move on now. Okay, so in this part of the video, we're going to go over SSL and TLS. Now, SSL and TLS are ways of doing encryption, and they were developed in order to do encryption between websites, web servers, and clients or browsers. SSL was originally developed by a company called Netscape. And if you don't remember, Netscape eventually spun off their source code and became Mozilla Project, where we get Firefox from. So back in 1995, Netscape released a version 2 of SSL, and there was a version 1, but nothing was ever done with it. So we got to version 2 of SSL, and that was used for encryption of web transmission between the server and the browser to do a whole number of flaws between the server and the browser. Now, SSL version 2 had a whole number of flaws, and SSL 2 has the type of flaws that can lead to decryption of messages without actually having the correct keys and not being the right endpoints. And so Netscape released SSL version 3 in 1996, And so we get SSL 3.0, which is better than 2.0, but it still had some issues. And so in 1999, we ended up with TLS. Now, SSL is secure socket layer and TLS is transport layer security. They both accomplish the same sort of thing, and they're designed for primarily doing encryption between web server and web browsers because we want to be able to encrypt the type of traffic. So let me show you what kind of traffic looks like. So first of all, let me open Wireshark. And out here, I already have a TLS scan ready for you guys that you can see. We have all sorts of TLS data. So you can see that here's my source and it's 1.32 and destination is 7612.4059.46, doing a client key exchange and the change cipher spec and an encrypted handshake message. And then we start getting application data. So there are some other steps involved here, and you're not seeing all of it with this particular Wireshark capture because, again, we get fragmented packets, and at some point it starts getting encrypted. And you can't see it anyways because Wireshark, without having the key, can't decrypt those messages. But what ends up happening is the client sends a hello, and the server responds with a hello, and they end up exchanging information as a part of that. Now, including version numbers supported, and you get random number, and the client's going to send out a number of cipher suits that may want to support an order, and it can support the server, and it's going to pick from those suite of ciphers. Now, then we start doing the key exchange and then do the change cipher spec and from the client and server, and eventually the server just sends a finished message. And at the point, we've got this encrypted communication going on, but there's this handshake that goes on between the two systems. And there's a number of different types of handshakes depending on the type of endpoints that you've got. But that's the type of communication that goes on between servers and the client one. Important thing about using SSL and TLS is, as I mentioned, some of the earlier versions had vulnerabilities in them, and you want to make sure that the servers aren't actually running those. So you want to run some scans to figure out the type of calls and ciphers that different systems use. So for this, we can use something called SSL scan. So this is available for Unix. I'm not really sure if there is something that is similar for Windows or Mac, but on a Unix-based system that is Linux, we can use SSL scan. So let me just show you how to use that. Clear this part out. So what we can do is run SSL scan again, suppose www.edurecord.co. So I'm going to do an SSL scan here against the website, and you can see it's going out and probing all the different types of ciphers that we know on this system. Start with SSL v3 and are going to TLS version 1. And we could force SSL scan to try to do an SSL v2. If I scroll back up, here I get the surface ciphers, which is SSL version 3. It's using RSA, and it's using RSA for the asymmetric. Now, in order to do the key exchange, and once we get the session key up, we're going to use AES 256, and then we're going to use the secure hash algorithm to do the message authentication, or the MAC. It's something called the HMAC for the hashed message authentication code. And what it does is simply hashes the MAC address that you would check one side against the other to make sure that the message hasn't been fiddled with in transmission. You can see here all the different types of cipher suits that are available. Here's TLS running RC4 at 40 bits using MD5, so that would be a pretty vulnerable type of communication to use. And between the server and the client, a 40-bit cipher using our C4 is a low-strength cipher, and we would definitely recommend that clients remove those from the supported ciphers that they have on their server. All that configuration would be done at the web server as well as when you generated your key and your certificates. Normally, certificates would be handled by a certificate authority. Now, you can also self-sign certificates and have those installed in your web server in order to do communications with your clients. The challenge with that is browsers today warn when they see a certificate against a certificate authority that is entrusted of it, and it doesn't have any certificate authority at all. So you'll get a warning in your browser indicating there may be a problem with your certificate. If your clients are savvy enough, and if the users are savvy enough, you may be able to make use of these self-signed certificates and save yourself some money. But generally, it's not recommended simply because clients are starting to get these bad certificates. And when they run across one that's really a problem, a real rogue certificate, they're going to ignore the certificate message in their browser and just go to these sites that could have malicious purposes in mind and may end up compromising the clients or your customers or users. So that's SSL and TLS and how they work and negotiate between servers.